satisfies, the remaining portion of the precipitation flows over the ground as a overland flow. Okay. After detecting all these evaporation losses and infiltration losses, still there is a precipitation. Then that precipitation flows as a overland flow and reaches the stream. Okay. Again the stream again it join the ocean. Okay. So once the water join the ocean, again from there it starts evaporating. That is the end of the hydrologic cycle. Okay. So this is the brief introduction of the hydrologic cycle. So evaporation, then condensation, then precipitation, even some portion is infiltrated into the ground. Okay. And it joins, if the infiltration is more, it percolate down and join the groundwater table. Even this groundwater also joins the ocean. Okay. So the water join the ocean. One is as a overland flow join that streams, and the stream join the ocean. Even groundwater also join the ocean, but it takes several days to reach the stream because the velocity of the groundwater is very low when compared to the overland flow, right? So this is the brief introduction of the hydrologic cycle. Okay. So one source of water for us is rain. For all, it may be for a reservoir, it may be a groundwater, it may be a lake, it may be a depression storage, whatever it may be. So today's topic, one of the topic in source of water is the reservoir. Okay. Uh, you know, as I said, when you construct a barrier across any natural streams, when you construct a barrier across any natural streams, then upstream side water get pulled up, right? So that pool of water is called reservoir. Okay. So the definition is water collected in a pool or it may be a lake, may be termed as reservoir, right? The upstream side of the obstruction, water gets pulled up, that is called reservoir, right? So that is a broad general definition of the reservoir. Okay. Why the reservoirs are constructed? Yeah, the main is when supply is less than the demand. When the supply is less than the demand, then we thought of storage of the water. If the supply is always greater than demand, there is no storage is required. You can directly use from the river. When we are getting flows throughout the year, every day, where the supply means the flows in a river is more than the demand, then there is no need of storage of water. So directly we can draw water from the river through the network of the canals and you can use it. But India is a semi-arid country, okay, where we have monsoon only for 4 months. 85, nearly 80 to 85% of the rainfall occur in these 4 months only: June, July, August, September. Next 8 months are non-monsoon periods. We will not get the rainfall. There the supplies flows in a river is less than the demand. Maybe in 4 months the demand is less than the supply, but the rest of the 8 months the demand is more than the supply. Therefore, we have to store the water those 4 months and use them for the rest of the 8 months whenever there is a need. That's why we need a storage reservoirs. Okay. So there during any specified time interval when supply less than the demand, then there is a need of storage. Okay. And also for drinking water, we'll construct the dams or reservoirs, maybe for irrigation purpose, and for hydropower generation, or for flood mitigation also. So these are the some of the purposes for which a reservoir is required. Right? So depending upon the purpose it serves, the reservoirs are classified in different categories, right? So the first one is called storage or conservation reservoir. So it is the when it retain excess water supplies during period of peak flows and release them gradually during low flows as and when the need arises. So that is called a storage or conservation reservoirs. Where the water comes into this type of reservoirs? From natural streams, natural rivers, right? The excess water stores and that water will be utilized whenever there is a need. Such type of reservoirs are called storage or conservation reservoirs. The next one is the flood control reservoirs. The main objective of this of reservoir is to mitigate the flood, to control the flood. The exclusive purpose of construction of reservoir is to protect the areas laying in the downstream side of the dam. One example in Andhra Pradesh, combined Andhra Pradesh is there is a dam constructed across a Musi river. There is Nizam Sagar project. 400 years back, maybe I don't know exact that time. So that when there was a heavy flood occurred in Hyderabad, lot of area was submerged. So that time the ruler was decided to construct a barrier across the river. So the main purpose, there is no irrigation at all, no power generation, no domestic supply of water. The exclusive purpose of that reservoir is to protect the Hyderabad city from the flood. So the objective of that reservoir is to protect the downstream area of the areas. So therefore that is called a flood control reservoir. Okay, you know what is a flood? Flood is when water overflows banks of the rivers, the surrounding area gets submerged. So that is called flood. Okay, so if you see the hydrograph, the peak is very high, the base period is very low. So maybe the amount of water may be the same if you increase the base period and decrease the peak, then it can safely pass through the river, right? If the peak is very high, the base period is low, what will happen? The surrounding areas get submerged. Okay, the main purpose of this reservoir is to reduce the peak and enlarge the base period of the hydrograph. So therefore that is called flood control reservoir. The main purpose of this type of reservoir is to control the flood. That is one objective. Right. So another one is the distribution reservoir. A small storage reservoir constructed within a city water supply system is called distribution reservoir. In this type of reservoir, this can be filled by water with some pumping the water from a river or maybe a canal. Okay, it is a small reservoir. Maybe the exclusive purpose is to supply water to a city. Such type of reservoirs is called distribution reservoir. We have one reservoir near Samalkot that is called distribution reservoir which supply water to the Canada city. And the fourth one is the multi-purpose reservoir. Okay, as the above three type categories are, the objective is single objective. If it is serves more than one purpose, if it is serves more than one purpose, then it is a called multi-purpose reservoir. Okay, besides flood control, if irrigation is taking place, besides irrigation and flood control, if it is used for generating the hydroelectric power, okay, beside all those three, there may be used for a recreation purpose, then this type of reservoir is called multi-purpose reservoirs. Nowadays all the projects or dams or reservoir being constructed with the aim of more than one objective. Okay, so this Nagarjuna Sagar is the multi-purpose reservoir. Srisailam dam is a multi-purpose reservoir. Even Polavaram is also multi-purpose reservoir. Right? If it serves more than one purpose, we call it as a multi-purpose reservoir. So another one is a balancing reservoir. The balancing reservoir is a small reservoir constructed downstream of the main reservoir for holding water and release from the reservoir. Okay, So where in the main type of storage or conservation reservoir, we can hold the water for a longer period. Maybe months we can retain that water in a reservoir. But whereas in the balancing reservoir, we can hold for hours or maybe 1 or 2 days. Okay. If there is a flows in a main dam, okay, fill this balancing reservoir, divert the water from the canal, fill this balancing reservoir, hold it for hours or maybe days, and again release it. Okay. So that is called a balancing reservoir. These are the four categories of reservoirs based on the purpose it serves. Yeah, this is a ethical diagram of a reservoir. You see the upstream side of the obstruction. It's a pool of water. Okay, that is called reservoir. Okay, the main obstruction is called what? Dam. So that is called the body of dam. It is connecting both banks, left bank and right bank. Okay, so I think it is a arch type dam. It looks a arch type dam, right? The top side is called generally upstream side, and the below is called a downstream side. Okay, and there is a spillway crest is there. Spillway is there. What do you mean by spillway? Spillway is a overflow section of a dam is called spillway. Okay, overflow section of a dam is called spillway. How do you release the water? We have maybe from the left bank and right bank we have a headworks. Okay, if there is a heavy flood occurs, how do you release the water? Through the spillway only. Sometimes if you observe in newspaper, in Nagarjuna Sagar gates, 2 gates were lifted. Okay, so where that water will go, it will go to the rivers, not to the canals. The excess water is released through the spillways. General operation, how the water is released from the reservoir into the canals? Through headworks. We have a left bank, there is one headwork, we have right bank, there is one headwork. Like in Nagarjuna Sagar, we have a left bank canal and right bank canal. So the water is released from the upstream side, a headwork is constructed, general operation. So whenever there is a demand in the downstream side to supply water to some other field for irrigation purpose, we release the water, not through the spillway. Spillway is when there is a heavy flood. Heavy flood is coming into the reservoir, the excess water is released through the spillway. So the spillway is defined as a non-overflow section of a dam is called spillway. So generally the spillway is a concrete gravity type. Okay, even dam sometimes it may be a earthen dam or it may be a concrete dam, or the combination can also be possible. So this is a typical diagram of the how the reservoir looks like. Yeah. Therefore, how do you select a reservoir? So there are a few points to select a reservoir. The first one is it should be a large storage capacity. Okay, large storage capacity, because economical point of view, if you construct a dam or a reservoir, it can store as maximum as possible. Such type of selection you should consider. Okay, so how do you consider? The topography of the site should be such that the reservoir has a large capacity to store water. Okay, right. The second point is it should be a suitable site for the dam. It should be a suitable site for the dam. A suitable site for the dam should exist on the downstream side of the proposed reservoir. Okay, so well, reservoir you have considered this is very suitable for reservoir, but at the same time you should see at the downstream side also the site should be suitable to construct a dam also. Okay, so both should be you have to consider, right? The reservoir basin have a narrow opening in the valley so that the length of the dam is very small. So the bank, the distance between the left bank and right bank of the canal should be as far as it should be minimum to reduce the length of the basin. dam. The cost of the dam is often a controlling factor in the selection of a site of the reservoir. The third one is water tightness of the reservoir. Okay. The geological condition of the reservoir site should be such that the reservoir basin is watertight. The reservoir sites having are not suitable. The reservoir basin having shales, slates, schists, gneiss, granites are generally suitable. Okay. So how do you the soil or below the reservoir should be a pervious in nature. If it is impervious in nature. If it is in a pervious in nature, what will happen? The infiltration will be more, therefore the losses will be more. Okay. So therefore, so this is also very important point. Next. Good hydrological conditions. Next point. The hydrological conditions of the river at the reservoir site should be such that the adequate runoff is available for storage. The catchment area of the river should give an high yield. There should not be heavy loss in the catchment due to evaporation, transpiration, and percolations. Where you will consider generally dam or reservoir, where we have a very good flows available. Okay, so there such type of streams should be selected. Okay, and also see that there should be minimum losses, evaporation losses, transpiration losses, and percolation losses. Okay, and that catchment should yield more amount of water. Such type of site should be selected. Deep reservoir. Deep reservoir is preferred than the shallow reservoir. What is the advantage of a deep reservoir? Because the water spread area is less, depth is more, water spread area is less. So therefore, the evaporation losses are directly proportional to the water spread area. Since the water spread area is a minimum, we can minimize the evaporation losses. Therefore, always prefer deep reservoir than a shallow reservoir. A small submerged area. Okay. The site should be such that the submerged area is a minimum. It should not submerge costly land and property. Okay. It should not affect the ecology of the region. Monuments of historical and architectural importance should not be submerged. So this is a very big problem in getting the permission from Minister of Environment. Okay. If the suppose a reserve forest comes under the submerged area, they will not permit. If a tribal area comes under the submerged area, you will not get the permission. Relocation of those people is very difficult. So even if you give a lot of money also, they have very some sort of attachment to the land they are living since years together. So it is very difficult to relocate them from that place to the another place. Even if you give very big bungalows also, they won't come. Okay? So that is the very biggest problem of today we are facing even in Polavaram also. Okay. So therefore, such type of sites in generally we should avoid. Right. And low silt inflows. So as you know, when there is a precipitation or maybe rainfall occurring, because of this kinetic energy, the impact of the water drop on the soil, on the earth, soil particle detached from the earth surface, and this soil flow along with the water, okay, and comes to the stream, okay, and these streams again join in a main river, and it will come to the river. So therefore, the sedimentation is the biggest problem in some rivers. If you construct a river across those streams, what will happen? After some time, it is not a collection of a pool of a water, it is a pool of sand. So therefore, first you study which stream is having more silt in water. Okay, avoid maximum such type of stream. Construct the dam upstream side of that stream. Okay, construct the dam upstream side of the that stream. If it is not avoidable, first you treat that catchment by constructing a small check dams, arrest the some watershed management, arrest the sedimentation there itself, not allow into the reservoir. Okay, so therefore always your dam site or reservoir site should be away, means upstream side of the catchment which is having the high silt in the water. Another one is not no objectionable mineral. If the very minerals are present in that area, objectionable mineral, so generally we should avoid such type of site. Last one is the low cost of real estate. The cost of real estate for the reservoir site, dams, dwellings, roads, railways should be low. So because 50% of the project cost goes to the this only, means land only. You have to have land from the farmers. Okay, and if you avoid such type of sites, the cost of the project will be minimized. So these are the some of the points we should keep in mind for selecting a suitable site for a reservoir site or dam site. So this is a typical diagram of the dam and the reservoir. Okay. This is the various levels of the reservoir. So what is the minimum pool level, normal pool level, maximum pool level. Okay. So normal pool level, generally it is the level in the reservoir when there is a normal operation is taking place. Can be allowed in the reservoir up to that level, normal pool level. Okay, and the minimum pool level is just sluice gate. The crest of the sluice gate level is called minimum pool level. Okay, so generally, in general, the water in the reservoir fluctuates from minimum pool level to normal pool level. When there is a monsoon period, the level in the reservoir may be at the normal pool level. During summer season, dry period, the water level in the reservoir may be in the minimum pool level. When there is a heavy flood coming into the reservoir, it can be allowed up to maximum pool level. It can be allowed up to maximum pool level. Therefore, how do you fix the levels? Normal pool level and maximum pool level. When you design a flood, means a 1,000 years flood or 100 years return period flood. Okay, if you assume that if 1,000 years flood is coming into the reservoir, okay, and if you know the capacity of the sluice, if you completely lift all the gates, okay, and you know the input into the reservoir, you know the output from the reservoir. If that is the case, what will be the levels in the reservoir? Okay, so based on that particulars, the level maximum pool level is fixed. Okay, if you underestimate the flood, what will happen? The maximum pool level will be will be not increased, will be lower, because the maximum pool level will be fixed based on the flood coming into the reservoir. If you underestimate the flood, what will happen? The maximum pool level will fix just lower than the actual levels. Okay, therefore what will happen? Your height of the dam is also up to that point, right? So when that flood has occurred, what will happen? Overflow takes place. Very danger to the structure. Even though if you completely open the all gates, it cannot safely pass through the spillways because you have underestimated. Okay, the excess water will be overflow through the body of the dam. Other portion, water will not flow through the spillway. Left side of the spillway, right side of the spillway will be overflowed because of the underestimation of the flood. So therefore, you have to accurately estimate the flood. And same time, if you should not overestimate the flood also. If you overestimate the flood, what will happen? the maximum pool level you will fix at a higher level than the desired level. Okay, so therefore you have to increase the dam. So if you increase the dam, the cost of the construction will be very high. Even for few meter of 1 meter, if you increase the dam, the entire the design will be changed. Base has to increase. Okay, so it cost very high. So it is not economical. So therefore, it should not be underestimated. It should not be overestimated. Okay, it should be correctly estimated. So based on the flood only, these levels are fixed. Flows, minimum pool level, normal pool level, and maximum pool level. So this is a zones of reservoir. The amount of water stored between the normal pool level and minimum pool level is called useful storage. It's called useful storage or active storage. Okay. The water stored below the minimum pool level is called dead storage. Okay. Why it is called dead storage? It is not useful to. It's not useful because if you see that sluice gate is above the minimum pool level, so water not be useful for downstream purpose. Okay. But that minimum dead storage is kept for what purpose? For sedimentation purpose. Even after 50, you estimate after 60, 70 years, only maybe the dead storage is filled with sediment. Okay, so you have to design the even fix the dead storage also based on the sedimentation coming into the reservoir. Okay, therefore sedimentation studies also should be done before fixing these levels. Okay. And surface storage is the storage between the normal pool level and maximum pool level. So that is called surcharge storage because it is not it is uncontrolled storage. Uncontrolled, this is excess storage. Okay. So after normal pool level, all the water will be let off from the reservoir through the sluice, through the spillway, because it is not useful. Okay. So generally we maintain the reservoir up to normal pool level. Okay. So the normal pool level is also kept generally at the crest of the spillway crest, right? And there's another storage also. It's called bank storage. Bank storage is when the reservoir is completely filled with water at the normal pool level. If the banks are of pervious in nature, what will happen? The water gets seeps into the banks. All the voids are filled with the water. When the water level in the reservoir falls to the minimum pool level, the water stored in the pores will be again back to the reservoir. So though the percentage of the volume of that amount of water is very less, sometimes it may be more, that depends on the nature of the banks. Okay. So that is called bank storage. Okay. So another storage is also there, that is called channel storage. Even before constructing the dam, some amount of water is available in the river. Okay, that called channel storage. Okay, so these are the various zones of the reservoir. There is a dead storage, useful storage, surcharge storage, bank storage, and channel storage. And the levels are minimum pool level, normal pool level, and maximum pool level. Yeah, investigation for reservoir planning. As you know, for there are three types of investigation for any engineering structures. So one is engineering survey, geological investigation, and hydrological investigations. Okay. What we'll do in engineering survey? We take the levels and prepare a contour map, maybe 5 meter interval or 1 meter interval. Depends upon the requirement. Okay. Once we have the levels for the entire area, then can you calculate if your dam height is let us say 100 meter with respect to the mean sea level, what are the areas going to be inundated? Can be calculated. Okay. If the dam height is 80 meters, what are the areas going to be inundated? Up to what contour? Up to 80-meter contour, all the areas going to be inundated if your height of the dam is 80 meters. Okay. So therefore, So this is useful for even to calculate the area of submerged areas, and even you can calculate the volume of water stored in the reservoir. Okay, and geological investigation, as we explained in previous section. So what are the faults, folds? What are the query sites available for constructing of the dam if it is an earthen dam? So these investigations should be carried out in a geological investigation. And hydrological investigations. So blindly you cannot go and construct a dam of any river. First we should study what are the flow patterns in the river. What are the flow patterns in the river? So last 50 years data we should have. Okay, and based on that one, if these are the flows available in the river, so we want to utilize maximum flows coming into the river. So what should be the height of the dam? Okay, what should be the yield from the reservoir? So that can be calculated using a hydrological investigations. Generally, this is a demonstrate a contour plan to a scale of 1:250 or 1:500 is usually prepared. The contour interval is usually 1 meter meters or 2 meter. The contour plan should cover an area at least up to 200 meter upstream and 400 meter downstream, and for adequate width beyond the two abutments. So that is the engineering survey for a dam site. If it is a reservoir, the scale is 1:15,000 and the contour intervals for 2 meter to 3 meter depending upon the size of the reservoir. Okay. So from this data we prepare a area elevation and storage elevation curves. Okay. For different elevation up to a elevation of 3 to 5 meter higher than the anticipated maximum water. So this survey is once you have a contour map available with you, okay, and you have a for this contour what are the area going to be submerged. If you know the vertical height is there, area is there, can you calculate the volume between the two contours? Using any Prismadile formula, Simpson formula, we can calculate the volumes. So therefore, we can prepare a graph between elevation versus storage. If this is the elevation in the dam, what is the storage? Can be easily calculated. If you know the vertical height and the area, and the volume can be calculated between two successive contours. Next. So this is a typical diagram. It is a elevation area volume curves. Okay. On the x side and y axis, it is a elevation above mean sea level, and x axis it is a volume. Okay. So this curve is the first curve is, see that, okay, that is the elevation versus volume curve, right? For any elevation, for the, so let's say minimum operating level, that's the minimum pool level, what is the volume can be calculated. So this is very useful for day-to-day operation of the dam or reservoir. Okay, suppose today the water level in the reservoir is let us say 75 meters. Okay, at the 75 meters on the y-axis elevation, I draw a horizontal line. Okay, and from the where it touches the curve, from there again draw a vertical line. Okay, then you can read the volume. Right. That is the amount of water available at present in the reservoir. Okay, so if you know the amount of water, how much water should be released to the irrigation, how much should be released to the domestic purpose can be planned, right? So this is very useful. So this curves will be revised once in a 20 years. Why? What is the reason? Why it changes? Because of silting. Okay, suppose for 75 meter from this curve, for 75 meter elevation in a reservoir, the volume may be, let us say, 10 million cubic meter. After 20 years, for the same 75 meters, you will not get 10 million cubic meter of water in the reservoir, because some portion will be lost because of the sedimentation. So therefore, again you have to do same survey, engineering survey. You have to prepare the contour map. Okay, because of the sedimentation some area gets filled up, right? So therefore these curves are revised once in a 20 years. Okay. So how do you do the survey once there is a water in the reservoir? But there are other techniques are there, like remote sensing GIS techniques are there. Okay. Even sounding techniques. Use the boat and take the vertical this jet value using some soundings. Okay. And you can prepare the contour maps. So these are the geological investigations. What geological investigation we do is suitability of foundation for the dam should be studied, and the water tightness of the reservoir basin should be studied, and location of the quarry sites for the construction material is also be studied under the geological investigations. The hydrological investigations study runoff patterns and to estimate the yield. Okay. And determine the maximum discharge at the site, that is the design discharge, flood discharge, to fix the various levels of the dam. So this is useful. Yeah, runoff pattern and yield. The most important aspects of the reservoir planning is to estimate the quantity of water likely to be available in the river from a year to year or season to season. Okay. So how do you estimate the flows in a means yield from the reservoir based on the absorbed data? First you should have a gauge site at that point. So gauge site is we will measure the flows in a river. Okay. So if you have the data, that data for the last 50 years, okay, analyze those data using any statistical method or any conceptual methods and estimate the yield from the river. Okay. If you know the yield, then you can fix the reservoir capacity. Right? Next. So this is a maximum discharge as a flood discharge can be estimated using a empirical relation, mostly correlated with the catchment area, if that, and any statistical methods, or there is another theory is there, unit hydrograph method, or you can do flood frequency analysis also. Okay. Usually for a big reservoirs, 1,000 years flood is taken for spillway design. Okay. Yeah. So that next one is determination of the required capacity. Determination of the required capacity. Okay. How do you determine the capacity? How do you fix the reservoir capacity? How do you fix the reservoir capacity? Huh? Depends upon what? What is the main factor? Demand. How do you design this hall? Based on the demand. Suppose if there is a one conference, maybe it should be accommodated maybe 150 to 200 members. Based on that one, we will design the room. So similarly, the reservoir capacity will be estimated based on the demand. A demand may be a irrigation demand, or it may be a drinking water supply for a municipality is another, and it may be a demand for an industrial purpose. Okay, all these demands should be calculated. So if for a specified time period, if this is the demand, to reach this demand or to meet this demand, what should be the capacity of the reservoir? That is our objective. First here is demand is fixed. So this is the demand we want. So to meet this demand, what should be the capacity of the reservoir? Understood? So that is the our objective. Next. So this can be solved using a graphical method. Graphical method is a mass curve. First we have to prepare the mass curve. The mass curve is a cumulative inflows against time is called mass curve. Okay. we have a 50 years data available in a river, cumulative every year what is the flows in a river, and second year, the first year plus second year is the cumulative inflow, and I draw a graph between cumulative inflow on y-axis and time on x-axis. You will get a graph that is called mass curve. Okay? Next. First you have to, this is the mass curve. The continuation line is called mass curve, right? It has a peaks and it has a trough also, right? So this is called mass curve. The mass curve is a graph drawn between cumulative inflows on y-axis and time on x-axis is called mass curve. Okay. So this is what we are going to do here is fixing the reservoir capacity. Okay, based on the known demand. Okay, and the same graph, you draw the demand curve also. So below one is the demand curve for 1 year. For 1 year, the demand is Mn. Okay, this procedure is when the demand is constant. When the demand is constant. For 1 year, the demand is Mn. Okay, the first prepare the mass curve, that is a cumulative inflows on y-axis and time is on x-axis. On the same mass curve, plot the demand curve also. So this procedure is for when the demand is a constant demand, right? Plot the demand and join the line, so that join the line demand curve. Okay, the demand curve, the slope of the demand curve gives what? The demand per time, right? Now on the mass curve, A is one peak and F is also another peak, and there is another peak also. At the peak point, I draw a tangent parallel to the demand curve. Peak point, draw a tangent parallel to the demand curve. So A is one peak, A, B is one tangent that is parallel to the demand curve. Understood? Similarly, at point F, there is another peak is there. From there, I draw a tangent parallel to the demand curve. Okay. If there is another peak at top, again you draw another curve parallel to the demand, right? So now, if you look this mass flow and vertical ordinate, maximum vertical ordinate of the tangent and the mass curve is CD, and for that it is HJ. Okay, the maximum ordinate is the minimum reservoir capacity to meet the demand. Okay, I will repeat again. So the first is, so this procedure is when there is a uniform demand. First I draw a mass curve. Mass curve is cumulative inflows on y-axis against time on x-axis. Okay, on the same graph, draw a demand curve also. For 1 year, the demand is Mn. Okay, and join the line that is called demand curve. Okay, now at the peaks of the mass curve, that is A and F, draw a tangent at A parallel to the demand curve. Similarly, draw a tangent at F parallel to the demand curve. Okay, the maximum vertical ordinate between the tangent and the demand, this mass curve, is CD, and for second case it is HJ. Okay, the maximum ordinate gives the minimum reservoir capacity to meet the demand. That is, for this is a CD and HJ, maximum of these two. Whether CD maximum then HJ, then CD is the minimum reservoir capacity. Okay, so what is meaning? Suppose at A, let us assume at A the reservoir is full. The reservoir is full. Okay, at E, So the water is, what is the accumulated water in the reservoir? DE. Water available, amount of or volume of water available in the reservoir is DE. Then what is CD? CD is the, yeah, means suppose again the flows are coming into the reservoir, it's start filling the reservoir at B point, again it is filled. Okay, so you remember that if you draw a tangent at A, it should cut the mass curve somewhere. It means that if A is full and again the reservoir is full at B. Okay, at F the reservoir is full, again the reservoir is full at G. If it not cuts the mass curve, it is means that the reservoir is not going to, never going to fill again. If it's cut the mass curve somewhere, the point is where the reservoir is going to be filled again. Okay, so the difference the between B and F is called spill. That is the excess water releasing through the spillways. Understood? Right. So this is the mass. This is the procedure when the demand is constant demand. When the demand is constant, the reservoir capacity can be calculated using a graphical method like this. Okay. Next. 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 When the variable demand, when the demand is not constant, it varies. So in earlier case, the demand is constant per year. Okay. When the demand is variable, so how do you fix the reservoir capacity? So draw a graph between mass inflow and demand on the same graph, because it's a demand is not constant, it also varies. Maybe in January it is more, February it is less, like that. The demand is also varying. Draw both the demand curve and mass curve on the same graph paper and find out the vertical intercept between the two curves. Okay, the maximum vertical intercept gives the minimum reservoir capacity required to meet the demand. Right? So this is the procedure when there is a demand is variable, not constant. This is the third case. Storage required when the demand is equal to the average discharge of the river. What do you mean by this statement? When the demand is equal to the average distance of the, sorry, average discharge of the river, it means that we don't want to waste a drop of water. All the amount of water available in the river should be stored, utilized completely. Okay, so that is the case, C case, right? So for this procedure is, this is the procedure. First, similarly, draw a mass curve. Mass curve is mass flows on y-axis and time on x-axis. That is a ADCFB. So that is a mass curve. Curved one is the mass curve, right? Draw the, join the line A and B. Draw a line joining the A and B. Okay, what it gives? Average flows in a river. Average flows in a river. Now at peak, highest peak of the mass curve, draw another tangent at D parallel to the this average flow curve. Okay. Similarly, at the lowest point C also, draw another tangent at C parallel to that curve. Okay. Now the vertical intercept of the top curve and below curve gives the storage capacity required to meet the demand. That is the average flows, yearly average flow in a river. Okay. So this curve shows that, suppose for the given, for that reservoir capacity, at 1950 at A, the water available in the reservoir is A dash. A dash is below, A double dash is top one. Okay. Then the reservoir is going to fill at D. Okay. Again it will be empty at C. Okay. Again it will be going to fill at B dash. Okay. Again it is not going to empty there. It is not touching the downstream line, downside line. Okay. Or assume that if the reservoir at A is completely filled. Okay. Full. The reservoir is full at A. Again it will be full at E. Again it will be full at F. Again full at K and B. Okay. Assume that if the reservoir is empty at A, the reservoir empty at A, again at E, again it will be empty at F, and it will be K, and it will be B. Okay. So these are the points you can read from this graph. So this is the procedure when we want to, the demand is indirectly fix the demand. The demand is, what is the demand? Sometimes you will get the problem like that. The demand will not, the figure will not give for demand. They says that there should not be any wastage from the reservoir, from the river flow. All the water should be utilized. Means all the water is utilized means the demand is combining the flows of every month divided by 12 is automatically the demand rate. Okay. So this is the procedure when the demand is given and you want to fix the reservoir capacity. So generally this is happen when at the beginning of the reservoir. At the beginning of the reservoir, we know the demand, we do survey. So these are the demand at this point, at this area, and to meet this demand we will fix the reservoir capacity. After 30-40 years, what will happen? Generally the reservoir capacity will be lost. Okay. Now the capacity is fixed. You cannot increase the dam height. Capacity is fixed. So for this capacity, what should be the yield from the reservoir? The reverse procedure, same reverse procedure. Okay. That can be also studied. And this fixing the reservoir for a given demand, that is the one procedure. Just we have discussed is the graphical method. That is a mass curve analysis. And another technique is also there, sequent peak analysis. So generally the mass curve approach is easy to use when short periods of data are to be analyzed. When the short periods of data is analyzed, mass curve techniques is useful. And this sequent peak analysis is a modification method of mass curve for lengthy time series. Analysis of for lengthy time series, particularly suited to computer coding. We have a 50-60 years data is with you, and drawing a mass curve for 50-60 years, you will get a lot of peaks, lot of troughs. Okay. So instead of doing those things, this procedure is very simple. You can do some coding, programming, and it will give automatically the results. Right. Next. So this is a graph. On y-axis, it is the flow minus demand. Every month we calculate the flow, average flow in a month and average demand in a month. Okay. That sum is plotted on y-axis. On x-axis, it is a time. Okay. So you will get the curve like this, peaks. Okay. If there is excess, top one, if it is a surplus, then low peaks you will get. The first one is the peak, and the subsequent curves are sequent peaks. Okay. So that maximum storage is a difference between the highest peak and the next immediate trough. Okay. It gives the maximum storage. So this is another procedure to fix the capacity of the reservoir. This is a reverse procedure determining yield from the reservoir for a given capacity. In earlier cases, what we fix the demand, and to satisfy this demand, what should be the reservoir capacity. The reverse case is capacity is fixed. So for this capacity, what should be the yield from the reservoir? Okay. The same procedure, but this is a reverse procedure. Same. Let me explain. This first, draw a masker, cumulative inflows on y-axis, again is time on x-axis. Next click. Okay. Now at lowest point, draw a vertical ordinate. What is that vertical ordinate? It is the storage capacity of the reservoir. Storage capacity of the reservoir. Okay, that is fixed. Here it is B, there also B, there is also B. Okay. Next click. Okay. Now we draw a tangent in such a way that it touches the vertical ordinate, top line of the vertical ordinate. Okay. At the peak, draw a tangent in such a way that the vertical ordinate is equal to V. Maximum ordinate is V. At the similarly, and another point also, next click. Draw another tangent. So that slope is D2. Okay. Maximum vertical ordinate is fixed. V is fixed. Right. Next. Another line at D. In everywhere, the maximum vertical ordinate is V only. But the slope is different. The first one is D1, next one is the D2, and next is the D3. Okay. Minimum slope is the minimum slope of that curve is the farm yield from the reservoir. Understood? Okay. That is the farm yield from the reservoir. In earlier case, we draw a tangent parallel to the demand curve. Okay. Then vertical ordinate gives the storage capacity. Here storage capacity is fixed. Therefore, vertical ordinate is first we draw, and from there top we draw a tangent. The slope gives the yield from the reservoir. Okay. So take the minimum value, that is the farm yield from the reservoir. Yeah, just reverse procedure. That is the farm yield. So D2 has a minimum slope. Therefore, D2 minimum slope. Therefore, that is the farm yield from the reservoir. So let us see one numerical example. Okay. This table gives the mean monthly flows into the reservoir every month. Okay. Determine the minimum storage required to satisfy a demand, including of all losses. The rate of demand is 50 meter cube per second. Okay. Here only monthly flows are given. The first column is month. Okay, from January to December. And the second column is monthly flows. In January it is a 60 meter cube per second, and in February it is a 50, like that. Every month the flows are given. The days in a month, January is 10 days, like that. The fourth column is calculated monthly flow volume. Monthly, this is the rate. The monthly flow volume, how do you calculate that? Fourth column. This is cubic day. Multiply this second column with the third column, you will get the fourth column. That is, I mean, 60 into 31. It is in 1860 is cubic days in month of January. Okay. Similarly, 1450 cubic day is in the month of February. Right. And then you accumulated volume on the last column, fifth column. Add 1450 to 1860, then 3310 is the in February. Okay. Now we have a cumulative flows in a river. Okay. Versus time. Can you draw the masker? Next. So this is the masker, right? That is a masker. Yeah. The same graph, the demand curve. What is the demand is given? Alright, there is a mistake here. 51 it was there, but actually it is 50. 50. And for 2 months, scale he has taken 2 months. So average 30.5 days in a 1 month. So 30.5 into 2, 61. 61 days and below one, if you see 2 months, and the vertical alternate that is P 61 into 50, that is yeah 3050 cubic day. Okay, if you join the curve PR, it is what? Rate of demand. Okay, now here we have only one peak. Okay, A, at one peak A, right tangent parallel to this demand curve, that is RP. Okay, that again now you measure the maximum vertical ordinate from that curve and maximum deviation from the mass curve. The maximum deviation from the mass curve is 2850. Okay, so that is what? That is required storage capacity of the reservoir to meet the demand 50 meter cube per second. Okay, is it okay? Next slide. Next. Yeah, this can be solved analytically also, not graphically. It can be solved analytically also. So this is another example. The yield of water in million cubic meter from a catchment area during each successive month is given. 1.4 million cubic meter in January, like that 2.1, 2.8, like that. Every month the flows in a river is given. So determine the minimum capacity of the reservoir required to allow the above water to be drawn off at a uniform rate, assuming that no loss of water over the spillway. The third example, as I said, take the demand is average flows of a river is demand. Okay, so demand, earlier case the demand is 50 meter cube per second is given. Here indirectly it is given. What is that? Average of all flows are the demand. So if you total yield of water in 12 months, add all those things, you will get 57.4. That is 1 year flows in a river. Okay, if you divide that value by 12, it gives 4.78 million cubic meter. That is the average rate of demand. So what is that? How you, if it is a if you want to solve this graphically, cumulative flows on y-axis, time is on x-axis, and join the first point and the last point. That gives what? Average flows in a river. Okay, at the highest peak, draw a tangent parallel to this curve. At the lowest peak, draw a tangent parallel to that curve. The deviation from the two lines is the required cost. That is the graphical method. The same can be done using analytical method also. Next slide. This is a first column is month, and second is the inflows in cubic meters, and the outflow is fixed. Calculated every month, the outflow is same. Every month is outflow is same, that is 4.78. Okay, and another two columns are deficit, surplus, and cumulative deficit and cumulative surplus. The deficit means in the first month the flows in the river is 1.4 and outflow the demand is 4.78. So it means what? Deficit month or surplus? Deficit. The 3.38 is deficit. And again second month also there is a deficit, and third month also there is a deficit, and fourth month flows in a river is 8.4, but demand is 4.78 only. There is a surplus. Okay, so place those values in the fifth column. 3.62 is the surplus. Similarly, fifth month, sixth month, seventh month is also surplus, and the rest from the 8th to 12th month are the deficit months. Okay, now you calculate the cumulative deficit and similarly cumulative surplus. 3.38, 2.68, 1.98 is 8.04 cumulative deficit, and cumulative surplus is 3.62, 7.12, 7.1.92. That is 20.78 is the cumulative surplus. Now you tell me, what is the minimum reservoir capacity to meet the demand? 20.78 is the minimum reservoir capacity. The maximum value in the last two columns gives the minimum required capacity. Okay, is it okay? That is about the reservoir. So far we have discussed about the reservoir definition and what is the classifications of various reservoirs, zones of reservoirs, and the investigations of the reservoir, engineering, geological, and hydrological investigations, and then selections of reservoir. How do you select the reservoir? And the next one is how do you estimate or fix the reservoir capacity to meet a particular demand? And that is there are three cases. One, there is a demand is a constant, and the demand is a variable, and the demand is average of inflows in a river. The three cases. And the fourth one is when the capacity is fixed, what should be the yield from the reservoir? So that can be done using mass curve and frequent peak analysis and also analytical. If you have any doubt, please ask. Any doubts? Any doubt? Any questions? Maybe useful to other students sitting in affiliated colleges. No questions? At least one question? General question? Okay. So next one is the groundwater. Another source of water is groundwater. What is the main source for the groundwater? It is again rain. As I said, some portion of the precipitation falling on the earth surface will percolate down. That is process is called infiltration. Okay. After meeting the soil moisture deficiency, if still there is a water available, it percolates down and join the groundwater table. Even the groundwater also moves from higher elevation to the lower elevations, but the groundwater velocity is very low, so therefore it has a takes several days, sometimes years to reach the streams. Okay, so therefore the main source of water is also precipitation. Okay, so where this groundwater stores in a pores of a rock. Okay, you know what is the voids? Where it stores in voids. If the voids are completely filled with water, this is called saturated. If it is partly filled with water and partly filled with air, it is unsaturated soil. Okay. So therefore, the occurrence of the the groundwater, the water available below the earth surface is divided into two categories. One is a vadose zone, or it can be called as a zone of aeration, or it can be called as a unsaturated zone. What do you mean by this? Unsaturated zone or zone of aeration or vadose zone is it's partly filled with water and partly filled with air. Okay, so that is called vadose zone, and below that it is called a zone of saturation or phreatic zone or saturated zone. Okay, so this means all the voids are completely filled with water. Okay, so therefore the water available in this zone, that is a zone of saturation, is called groundwater. Okay, the water available above this zone, that is the zone of aeration, is called vadose water. It's called vadose water. Not written. It is called vadose water. The water available in the zone of saturation is called groundwater. The water available in the zone of aeration is called vadose water. Again, that is divided into three categories: soil water, an intermediate zone, and capillary water. that soil water is the zone is very important for agriculture purpose, where the plants takes water from that zone only. Okay. Now the capillary water is even groundwater during because we have a capillary action. Some of the groundwater may raise up. Okay. So up to that point, that level is called capillary water. The zone between soil water and capillary water is called intermediate zone. So this is a vertical distribution of groundwater. Okay. You might have heard the aquifer. Okay. Aquifer, the definition defined as formation that contains sufficient saturated permeable material to yield significant quantity of water to well. So that is called aquifer. Okay. As I said, the water stores in a voids. If the voids are interconnected, it not only stores water, it also gives yield. Okay. If the voids are not interconnected, it neither it can store water nor it can yield water. Okay. So therefore, there are different types of rock formation. So one is a aquiclude. So that is a geological formation which can only store water but cannot transmit significant amount. Clay is the example. Okay. Aquifuse is it's neither store water nor it gives yield because the voids are not interconnected. Okay. So that is called aquifuse. Aquitard is the yield is very low when compared to the aquifer. Stores water, but yield is very low. So these are the different uh, rock formation: aquifer, aquiclude, aquifuse, and aquitard. Some of the properties of the aquifer: one is porosity. Okay, the porosity is the ratio of volume of voids to the total volume of the soil mass. Okay, so this property tells you the measure the how much water it can store. The porosity tells you the how much water it can store in a aquifer, because if the voids are more, it can store more water. The voids are less, it can store less. The porosity is more means what? Voids are more, therefore it can store more water. The porosity is less means voids are less, therefore it can store less water. Okay. Porosity tells you the amount of water it can be stored. Okay. But it does not tell you the amount of water it can yield. But there is a difference between amount of water it can store, amount of water it can yield. Okay. So this the amount of water it can yield is the specific yield. So that is a as the all water stored in the voids cannot be drained out using gravitational force or any other using mechanical device pumping. Okay. Only we can drain some amount of water. The rest will be there in the voids only using some chemical attraction. Okay. The amount of water it can drain in percentage to the total volume of the saturated aquifer is called specific yield. So the definition of the specific yield, the volume of water expressed as percentage of the total volume of the saturated aquifer that can be drained by gravity is called specific yield. The amount of water retained there itself is called specific retention. So there is a relation between these three properties. Porosity is equal to specific yield plus specific retention. Okay. So all the water stored in the water cannot be drained out. Only we can drain some portion of the water. The rest will be attached there itself in the voids because of the some chemical bonding between the voids within the voids. Okay. The amount of water can be drained with the ratio as a ratio with the total volume of the soil is called specific yield. The amount of water retained by retained in the voids is called specific retention. The porosity is equal to specific yield plus specific retention. Okay. So these are the some of the values for different clays. We see the clay, the porosity is 45 to 55. For the sand, it is 25 to 40. What porosity tells you? Yeah, if you see this porosity property for clay, it is 45 to 50. When compared to sand, it can store more water. But the specific yield for the sand is more than the clay. Specific yield is 1 to 10 of the from the clay, but for the sand it is 10 to 30. Okay, right? So there is a that is the difference between the porosity and specific yield. Next, again there are four types of aquifers. One is unconfined aquifer, confined aquifer, perched aquifer, and leaky aquifer. Okay, what do you mean by the aquifer? It's a ground, huge aerial extent. మన కింద అంతా ఉన్నది ఇట్స్ aquifer. Okay, so just let me explain different types of aquifer using this diagram. So this is a, let us say, ground surface is there, one line, right? Sir, no, pie line. So అది ఆ line కింద dot of the కింద, yeah. So that is the ground surface. Okay, that is the ground. Below that ground, the formation will be like this. Okay, and this one hatched line, that is the confining stratum. Okay, and again down hatched line is also confining stratum. The hatched line is what? It is an impervious stratum. Impervious stratum. Okay, there are one impervious, below the aquifer is there, bottom is there is an impervious layer, and that is the ground surface. Okay, so the unconfined aquifer is, and in unconfined aquifer there is a dotted line is there, dotted line, that is that dotted line, yeah, move it, yeah. So that is groundwater table, that is called groundwater table. So one, you see the vertical distribution of the groundwater table is below that one completely saturated. If the upper surface of the saturated is groundwater, the groundwater serves as upper surface of the aquifer, that is called unconfined aquifer. Groundwater table, if you see any open well in your home or in any field, so you will see the water level, so that is the groundwater level. Okay, the groundwater table here serves the upper surface of the saturated aquifer, then that is called unconfined aquifer. Okay, and down one between the two impervious layer, that is called confined aquifer. So here the water in the confined aquifer is under pressure, it is above the atmospheric pressure. It just like a flow through a closed conduit. In fluid mechanics, if you study, flow through a closed conduit, the pressure inside the flow, inside the pipe, is above the atmospheric pressure. Okay, so you can assume that it is a closed conduit, because an impervious layer is just like a pipe. So therefore the pressure, water pressure in a confined aquifer is the above atmospheric pressure, but the water pressure in a unconfined aquifer is atmospheric pressure. Okay, if you dig a well into a unconfined aquifer, the first one is dig a well, okay, right circle, yeah, yeah, well, if you dig a well in a unconfined aquifer, the water level in the well is up to water table. Okay, right? That is up to water table. But if you dig a well in a confined aquifer, the first two wells. So that first well is first well. Yeah, first well. So that is called well. Hmm. So this is the well driven into a confined aquifer. Okay, and this is the another well driven into a confined aquifer. Both first two wells are driven into a confined aquifer, and the last that well is driven into a unconfined aquifer. Okay, that well is called water table well. That well is called water table well, and these called artesian wells. The well driven into a confined aquifer, that is called artesian wells. Okay, so if you see, as I said you, the confining aquifer is similar to the flow through a closed conduit. So if you insert a piezometer at different locations, what will happen? The water rises into the piezometer. At what level it rises? That depends upon the pressure at that point. Okay. So let us say if the pressure at that point is 1 meter head, 1 meter head. Okay. So therefore your piezometer should be more than 1 meter head. So if your piezometer is 2 meter, meter is just like a glass tube inserted on a pipe. If your piezometer is 2 meter, the water in that piezometer rises up to a level of 1 meter, since the pressure at that point is 1 meter head. Okay. If your piezometer height is, let us say, 0.5 meter, what will happen? What will happen? Overflow takes place. Overflow takes place, isn't it? So what is the hydraulic gradient line? Hydraulic gradient line, an imaginary surface drawn above the piezometer levels. So this means what means? It means that the pressure at that point is that much only. If your piezometer is less than that one, what will happen? Overflow takes place. If your piezometer is 2 meter, it can raise up to 1 meter. If your piezometer is 0.5 meter, what will happen? Overflow takes place. So that's what happened in the first well. The actually the pressure at the confining, the pressure at this confining point, that is the dotted line on above the ground surface, is called piezometric surface. Are you following? Piezometer, that's what a piezometer is, an imaginary line drawn on drawn on surface of the water levels in each piezometers. Okay, piezometer. If you see the how do you measure the pressure in a pipe, in a flow, we have a simple manometers. Manometers are there, just like piezometer means manometers. Differential manometers, single tube manometers are there. If you have a pipe closed conduit, okay, like let us say 10-meter pipe is there. Okay, first one meter each interval, insert a manometers. Okay, and the water level raises into the manometers. Okay, I draw a line top of the water levels in the manometer, that is called piezometer. If you see the Bernoulli's equation, then what is the total energy is equal to P by P by W plus V square by 2Z plus Z. P by W plus Z is equal to what? Is a hydraulic gradient line. If we add the V square by 2Z, that is total energy line. Okay. So similarly here also, suppose let us say at this point where my cursor is blue cursor, the pressure at this point is up to that level. Okay, up to that level. Similarly, So that is the piezometric line. Piezometric line. From here to here, from that point, blue point to here, the piezometer line is above the ground level. Okay. The here the piezometer is the below the ground level. As I said in earlier example, if your the pressure at particular point is 1 meter height, if you insert a manometer of 0.5 meter, overflow takes place. So therefore, similarly here also the piezometer is above the ground level. So therefore, if you dig a well in a confined aquifer where the piezometric surface is above the ground level, the flow takes place in a well without any energy. Okay, there is no motors are required to lift the water. It overflows automatically. That well is called flowing wells. That well is called flowing wells. If you see any flowing wells anywhere, who have seen? Ah, springs. Where? That is I think different. The flowing wells. This is the concept of the flowing wells. No mechanic. Suppose if you want to lift the water in a water table well, the water table is up to this point and some mechanical energy or some energy is required to lift the water. Here there is no energy is required, it automatically flows because the piezometric surface is above the groundwater surface. So that well is called flowing well. Okay, that well, any well driven into a confined aquifer is called artesian well. Okay, the major difference between a unconfined aquifer and confined aquifer is it is a see here in a well dig into a unconfined aquifer, the water level is up to water table. So if you keep on pumping or if there is no recharge into the well, what will happen? It will decline, it fall down, drawdown takes place. If there is a recharge, rain is there and you are not lifting the water, it raises. So it raises when there is a recharge, it falls when there is a no recharge. The rise and fall of the levels in a well driven into a unconfined aquifer is because of the volume of water stores in a unconfined aquifer. Okay, understood this point? The rise and fall of water levels in a well dig into a unconfined aquifer is because of the volume of water stores in a unconfined aquifer. Okay, whereas in case of a confined aquifer, the rise and fall is because of the not volume of water stored in a confined aquifer, it because of the change in pressure. Because of the change in pressure. That is the major difference how you can distinguish between a confined and unconfined aquifer. Okay, there's 2 points. For unconfined aquifer, the top level groundwater table serves as the upper surface of the saturated aquifer, and also the rise and fall of water table in a well is because of the volume of water stored in a unconfined aquifer. That is an unconfined aquifer. Whereas in a confined aquifer, it because of the change in pressure rather than change in the volume of storage. So that is the two difference. That means the difference between a. So see how the unconfined aquifer is recharged. So here it recharge somewhere, it exposure somewhere. Okay, so it cannot recharge, but unconfined aquifer is through infiltration. Okay, so therefore, suppose if you want to look at a dumping sites, you want to dump a waste, municipal waste. So generally, you should avoid this area. What will happen if you dump the site? If dump the all waste in that pot, it will recharge. Okay, all the water in the confined aquifer get polluted. So generally, you should avoid such type of areas. Next. That first one is a difference between unconfined and confined. So it is another one is the perched aquifer. The perched aquifer is this is the perched aquifer. This is the perched aquifer. Okay. So this is a small groundwater aquifer above the main groundwater table. So this is the groundwater table. Above the main groundwater table is a small aerial extent. Okay. The below one is a impervious rock is there. That's why the water is not infiltrated down. It's just like a ball. So it is small aerial extent. Okay. So that is called perched aquifer. Okay. So the if you dig a well in a perched aquifer, after a few days it get dried up because it is a very small aerial extent. The recharge is there is no recharge after that. Okay. Next one. So this is a there are two terms. So one is a storage coefficient and another one is the storavity. Okay. These are the these two terms can be defined as a storage specific yield Sy and storavity S. Okay, take a 1 square meter area, unit area. Okay, so here if you look the first diagram, so that is the see initially the original water table is top. There is a original water table and it falls 1 meter below. Okay, so that amount of water it yields for 1 meter fall in the groundwater table is called specific yield or storage coefficient. For unconfined aquifer, the storage coefficient is nothing but the specific yield. You understood? The amount of water it can yield for 1 meter decline in the groundwater table or the amount of water it take into storage for 1 meter rise in the groundwater table. 1 meter for 1 meter rise, how much water it take into the storage? Or for 1 meter fall, how much water it can yield from the storage? So that is called storage coefficient. If it is an unconfined aquifer, the storage coefficient is nothing but the specific yield. For confined aquifer, it is called storavity. Next. So these are some groundwater surface water interaction. The first, if you see the first one, when the groundwater table above the bed level of the any stream, what will happen? It is called gaining stream. It called gaining stream. The groundwater table contributes to the flows. Even if you see some rivers, even though there is no rainfall, some flows available in the river. It is because of the groundwater. Okay, so that is the first case. And the second case is if the bed level of the river is above the groundwater table, the river from the water in the river contributes to the groundwater. That is called losing stream. Okay, so when it loses completely, it's called dry stream bed. Okay, these are some groundwater and surface water interaction. Next. Next. A small example, one two example, then I will conclude this unit. It's groundwater. So this is a 100-hectare area is there. The water table dropped by 4.5 meters, and the porosity of that soil is 30%. Find out the specific retention. And specific is 10%. Determine the specific yield and the change in groundwater storage. How do you calculate? If you see the statistics of the in a district, they used to calculate the groundwater storages in different mandals. What is the groundwater storage in a East Godavari district and in Kakinada mandal, like that? Okay. How do they calculate the groundwater storage? It's just like if you want a tin, if you take a tin, how do you calculate the amount of water available in the tin? If you know the cross section area and height, volume, simple volume. So similarly in ground also, If you know the area of the aquifer and there is a change in the groundwater table, let us say today is a 10 meter with respect to the top level and it falls to let us say 15 meter. What is the change? 5 meter. So area into 5 meter, it gives the volume. Okay, but it's not like a water in the tin. Where the water stores in the groundwater? Only in the voids only. In not only full voids, only specific yield. Therefore, you have to multiply that into specific yield. The amount of water available in any aquifer, any area, is equal to area of the aquifer, change in water level into specific yield. Okay, so that is this problem. Change in groundwater storage. Porosity and specific yield is porosity minus specific retention 20%, and the groundwater storage is area of aquifer into drop in groundwater table into specific yield. Okay, another example. Any question? Next example. Last. Okay, so this example is there is a area is there and there is a piezometer surface fluctuates from 19 to 9 meter and storage coefficient is given, and there is one well is there. That yield of that well is 30 meter cube per hour and it operates about 200 days. My question is, to complete utilize the groundwater, how many wells should be dug? Okay, so first you have to calculate the what is the groundwater storage available in the area. So groundwater storage, as I said, area into change in piezometric surface into specific storage coefficient. This is a, let us say, confined aquifer. This is a S value. If it is an unconfined aquifer, it is SY, right? So that is the 6.4 million meter cube is the amount of water available in that area. First calculate annual drop from the one well. How it operates? The yield from one well is 30 meter cube per hour. Okay, 30 meter cube per hour into 24 per day into 200 days. So that is 0.144 million meter cube. That is the yield from one well for 200 days. Okay, the total groundwater available is 6.4. One well can yield much. So therefore 6.4 by 0.144 is 44.5. If you dig 44 wells, you can completely utilize the amount of water available in the ground. So this is the simple calculations, right? So if your wells are more than 50 or 60, what will happen? The groundwater level completely declines. Okay, it may sometimes it may not recuperate back. Okay, there is a wastage of money also. Okay, so like that you can calculate the amount of water stored in the groundwater. Okay, so thank you. Yeah, okay. That first one is for piezometric surface, as I explained. Then imaginary line drawn on surface of the water levels in each manometer is called piezometer. So that is from the base, as if you know the Bernoulli's equation, energy equation, P by rho g plus Z is piezometric, that hydraulic gradient line. That ordinate is called piezometric, right? Okay, so that is that one. And reservoir, why is it necessary that contour plan is 1 is to 15,000? Okay, yeah, you know what is scale? He said the scale is 1 is to 15,000, but the answer, simple answer is there is a guidelines by Central Water Commission for you want to plan a reservoir. First you had prepare a map for 1 is to 50,000 scale. There is no specific rules for this one. These are guidelines given by the agencies. Okay, the scale is, this is generally, if you see the Survey of India topo sheets, you will find Survey of India topo sheet for 1 is to 50,000. 1 is to 250,000. Okay, so 1 is to 50,000 and this is 1 is to 15,000. Which is the highest scale? One is to 50,000 is the small scale when compared to this one. This is the highest scale. 1 is to 15,000 is the highest scale. What is the meaning of this one? 1 is to 50. 1 centimeter on the paper. So therefore that is small when compared to this one. The biggest scale is this when compared to that one. Okay. So that is otherwise we cannot prepare a big map. That's why we reduced one. So there is no specific rules. So these are the some of the guidelines given by the Central Water Commission. Any this only. Thank you.